Hello, everyone. First, thank you to Andy, Andrew, and Simon for allowing me to speak tonight. I'm Matt Hobbs, and I work for the UK Government Digital Service as head of front end. As well as front end, I also have a keen interest in web performance optimization. But today, I'm not here to talk to you about the wonderful world of UK government services, although I'm sure you're all really disappointed. I'm here to talk to you about a tool you may or may not have heard of, and that is WebPage Test. This talk is mainly about a very specific part of WebPage Test, and that is the waterfall chart. Now, the chart may look intimidating at first, but once you understand it, the visualization really unlocks a heap of information for you at a glance, allowing you to quickly debug issues, certify that issues have been fixed, understand how exactly a browser loads a page. There are a couple of bits of assumed knowledge for this talk. So first is the WebPage Test URL. So for those who are unsure, this is it. This will bring you to the public instance of WebPage Test, where you can test your site's performance for free. Second is that you have run a test. Don't worry though, if you haven't run one, I just so happen to have a whole blog post all about it, and you can see it right here. It's a shameless plug, I know. So first, let's cover a little background info about WebPage Test. What is WebPage Test? WebPage Test is a synthetic performance testing tool created by Pat Meenan in 2008 while he was working at AOL. It was originally an IE plugin called Page Test before evolving into the online version we see today. WebPage Test was recently acquired by Catchpoint in 2020. So Pat, along with the rest of the Catchpoint team, will help maintain and grow it into the future. But for the past 13 years, the public instance of WebPage Test, including all of the Dulles test devices, have been sitting in Pat's basement. This image is from 2014, and I assume Pat's basement may have changed in the past 6 years. So WebPage Test allows you to run web performance tests from any of these locations in the world. You can configure test agents to test your site using a whole host of browsers with many different connection speeds. The data you get back from the tool is invaluable for spotting and fixing web performance issues. Enough about the history of WebPage Test. Let's dive right into the waterfall chart user interface. So here's a basic WebPage Test waterfall chart. The test is from my own blog. This chart is essentially a visualization of the raw data you get back from various browser APIs. I've split this image into 7 sections. I'll go over each one very briefly. Number 1, the key. Here we see a series of colors. First, a set of browser and connection events like wait, DNS, connect, and SSL. Next, a set of color-coded files by their MIME type. You'll see 2 color tones for each. I'll come on to what this means a little bit later. And last, in pink to the right, the JavaScript execution time. Each of these colors corresponds to an event or request you'll see on the request timeline. Number 2, the request list. Here we see a list of assets found on this particular page. They're in the order that the requests go out over the network. The HTML in this instance is at request number 1 at the top. But this isn't always the case. Redirects and OCSP lookups can sometimes come before the HTML. Number 3, the request timeline. Here we see the waterfall. It looks much like you would see in the network tab in your developer tools. The color coding we saw earlier in the key applies here. Each asset is on its own separate row. The time in seconds is seen along the top and the bottom of the image. This could be in milliseconds for some tests as well. But there's a whole lot more going on in this image that I'll cover soon. Number 4, CPU utilization. Here we see a line graph of how much load the CPU of the test device was under at any point in time during the page load. It ranges from 0 to 100% utilization. It's always a good idea to keep an eye on this chart, especially on low spec devices. This is to see if the CPU is becoming a bottleneck for performance. Number 5, bandwidth in. This graph gives you an idea of the data flowing into the browser at any point in time during the page load. The absolute scale isn't particularly accurate, but it's roughly related to the max bandwidth allowed on the connection. In this example here, the max bandwidth is 1,600 kilobits per second, and this equates to a 3G connection. You mainly want to use this graph to check that the browser is doing useful work, rather than being wasted during the load. There's a much more accurate option called a TCP dump. This is located under the Advanced Settings tab when you configure the test. You should enable this if you want more accurate results that you can then examine using tools like Wireshark. Number 6, the browser main thread. So this image isn't taken from my blog since it's only a very small static site. It's nowhere near as busy as this. This is actually taken from one of the popular news websites here in the UK. Each of the colors corresponds to a particular task that the browser main thread is doing at any point in time. The y-axis corresponds to the percentage of time that the task is taking up. This graph is a great way to spot where the CPU is becoming a bottleneck and what task is causing it. Also note that these colors may look familiar if you've used the Performance tab in Chrome DevTools, as that's where they're copied from. And last, number 7, Pages Interactive. This thing bar gives you an indication of when the browser main thread is blocked. If the main thread is blocked for 100 milliseconds or more, the color will be red. If not, it will be green. Note that a blocked thread may impact on inputs like button presses, but browser scrolling is likely to be unaffected as this is handled off the main thread. So now if we pull all this together again, this UI should hopefully now make a little more sense. You could think of this graph as a story of how a browser is loading a page. So chapter 1 is first connecting to the server. Chapter 2, the downloading and parsing of the HTML. Chapter 3, requesting the additional assets. Chapter 4, pixels are rendered to the page. And the final chapter where the story ends is the finalized page with all the assets loaded. So let's pull out some specifics for the waterfall you can see on the slide here. First, let's focus on request number 1. We see a connection to the server. We see the HTML and download being downloaded and parsed, shall I say. The additional page resources are found and queued for later request. Note that the pink lines mixed in with the blue asset color of the HTML. This is JavaScript execution happening during the HTML download and parsing phase. Or in other words, the HTML page has 2 large chunks of JavaScript in the page source. In this test, under HTTP2 conditions, on request 14, we see an additional TCP connection being established. So this must be due to the asset requiring a cause anonymous connection, since the exact domain has already been used to download other assets on requests 2 to 5, using the connection already established on request number 1. Next, request 18, another TCP connection, and the color of the asset is in blue. This is a request for another HTML page, most likely triggered by some JavaScript execution. Now, the reason why I said it was triggered by some JavaScript is because notice where the TCP connection starts. It lines up with the inline script execution within the HTML on request number 1. So there's a very good chance that this is what initialized it. Also notice how busy the CPU, bandwidth, and main thread graphs are. This page is really working this device in all areas. Now, that's all not always necessarily a bad thing. That could just be a lot of useful work happening during the load. You may have also noticed a set of lines in different colors vertically down the page. These lines are specific events that happen during the page load. In the example on the slide, we see the start render in green at 0.6 seconds. Here, the first pixels are painted to the screen. DOM interactive at 1.75 seconds in orange. HTML has been parsed and the DOM has been constructed. Document complete or the onload event has fired at 5.5 seconds. So static image content has loaded, but changes triggered by JavaScript execution may not be included. There are other lines that aren't on this chart, but can be seen in the key above the waterfall on screen. So look out for those too. And finally, the request details panel. Each horizontal row is an asset request. If you click anywhere on a row, a panel will pop up with a heap of information specifically about the selected request and response back. Basic details like protocol and timings, all the way through to request and response headers. If you're looking for all these details in a large JSON blob, then the raw details panel would give you this. Using this panel for each request, you can really dig down into the finer details of the page load. So now we've gone over the basic layout and what it all means, let's look at some more advanced examples and point out some other features. Using WebPageTest, it's easy to examine the difference between HTTP 1.1 and HTTP 2. It's a good example to focus on as it's really easy to spot the differences. So both of these tests are from testing.gov.uk on desktop Chrome using a 3G connection. So first, let's look at HTTP 1.1. Notice the multiple TCP connections in red. Notice how eager the connections are on requests 3 and 4. This is default behavior for browsers under HTTP 1.1, where it creates multiple connections early in anticipation for downloading multiple assets. There's 2 DNS lookups shown in red, which are then reused for the other TCP connections shown in green. What is known as download chunks can be seen heavily on requests 5 to 7 and 17 and 18. So what are download chunks? This is where the 2 color shades I mentioned earlier come in. The lighter color at the start is the time at which the browser sent the request to the server. The dark chunks are data coming back from the server for this particular request. You may be asking what the yellow weight bars signify. So this is the point at which the HTML has been parsed, but the request for the asset has yet to be made. You can see this in the waterfall by looking at where the HTML ends and the start of the yellow weight bars. In this case shown here, the weight is because there are probably no pre-established TCP connections to make these additional requests. Also notice how the bandwidth chart has empty sections missing from it. In this example, we have a separate TCP connections fighting for limited bandwidth. But even with multiple TCP connections, the bandwidth isn't fully utilized. And this is what I meant by the term useful work. By making sure the network connection is fully utilized during this important loading phase, it should in theory improve performance by maximizing the number of bytes received by the browser. Now let's compare the exact same page, browser and connection under HTTP 2. First thing to mention is how overall the waterfall looks a lot cleaner. There's now only a single TCP connection on request number 1 used for downloading all the assets. There's not much download chunking as prioritization is happening over a single connection. Under the hood, Chrome sets an exclusive flag for the stream dependencies on each resource. So it downloads the assets in order from a long internal list. Here's an interesting observation. We seemingly have a single rogue DNS lookup on request 17, but it has no associated connection and SSL negotiation or the orange and pink colored bars. This is actually HTTP2 connection coalescing in action. The assets domain and the root domain are on different domains, but they are on the same underlying infrastructure. They both share the same IP address and SSL certificate, so the browser can use the existing TCP connection and SSL negotiation that was established on request number 1. Therefore, all the assets will download over the same single connection, even though they're on separate domains. Note that the bandwidth from 1.1 to 3 seconds is maxed out. We don't have the gaps over this time period like we did with HTTP 1.1. And this is essentially useful work being done by the connection. If I quickly flick backwards and forwards between the two, you really get to see the difference between the two waterfalls. Here we see that WebPageTest has exposed the internals of how the browser downloads a page under specific conditions. If I were to run the same test through Firefox or Internet Explorer, this picture would look very different. Now, briefly going back to the subject of download chunks, there's a very simple way to see the data that powers the chunk visualization. Clicking on the request you want to examine, you'll see a raw details tab. And this is one I mentioned earlier. The tab gives you all the JSON related to this particular request. Scroll down in this tab and you'll see a chunks array. This array contains multiple objects. Each object contains a timestamp of when the chunk completed, not started, and the number of bytes downloaded in this chunk. WebPage Test works backwards from the completed time. It then looks at the number of bytes downloaded and the available bandwidth at the time to calculate the chunk width to be displayed in the visualization. Next up are error and status codes. So WebPage Test will make it very obvious when it encounters a status code other than 200. Just a brief note on the chart used in this example. It's very easy with JavaScript and asset-heavy pages for a chart to be hundreds of requests long. In the example, many requests have been omitted from the waterfall chart to make it more readable. These omitted requests can be identified by the 3 dots highlighted in green. Look for the Customize Waterfall link under the waterfall diagram to do this. Back to our error and status codes. So requests 1 to 10 are all fine. They're all 200 status codes. Requests 99 and 101 are error codes, and the red background may have given this away. In this case, they are from a 400 response code, which refers to a bad request. The status code is seen in brackets after the request timing data. The timing value seen is the time taken to complete the request. This includes a TCP connection negotiation if it's required, but excludes wait time. Requests 123 to 130 are 302 status codes and are seen with a yellow background. The 302 code is the found but temporarily moved status code. Notice how the browser still has to set up expensive TCP connections in a few instances just to receive this 302 status code. This is certainly something to watch out for when you use third parties. Next up, a recent addition prompted, I believe, by Andy Davies. Each request comes with a document value in the details panel that tells you where the request was initialized from. So requests 2 to 5 are initialized from the root document. This can be seen as the text is black. Requests 11 and 28 are for new HTML documents. The text is blue to signify they have a new document value. So the request was initialized from somewhere other than the root document. This is most likely an iframe in this instance. Notice further down, requests 47 to 49 are also blue. These are assets being downloaded by the iframe. So the blue request text doesn't only happen with iframes, it also happens with service workers and all the assets that they load. And here's how it's displayed in the details panel when clicking on the requests. The top image, we see the root document. The bottom image is a third-party iframe from Google with a different document value. I mentioned the pink lines for JavaScript execution earlier. The JavaScript execution can be seen in pink on the request row, which triggered it. In this example, we see a solid block of pink. But is this very intensive JavaScript running, or is it short but fast repeating execution? Looking at the page's interactive bar below, it gives an indication in this example since it's solid red. But a recent addition, recent modification to JavaScript visualization has made this feature even more useful. Now, when the JavaScript execution is rendered, you don't always see a solid block of pink. The height of the pink bars indicates how quickly the JavaScript ran. So fast but frequent JavaScript execution will have very short height bars. So they no longer dominate the view. It's also worth noting that this functionality is only available in Safari and Chrome-based browsers. Firefox doesn't expose this information. Now, wouldn't it be great if you could add your own custom markers to the waterfall chart to see where certain events during the page load? It's actually fairly simple. Just use the mark method in the user timing API and add it to your page code. These marks will be shown on the waterfall as vertical purple lines. Note that the user timing marks don't show up in the default waterfall chart on the public instance of WebPageTest, but if you have your own instance, these can be enabled by default. So the only way to see them on the public instance is to view the waterfall using the customize waterfall link below the waterfall chart, which I mentioned earlier. And this is the view you can see in this slide. The reason for this is because many third parties leave these marks in their code, meaning there will be a lot of noisy looking waterfall charts when using third parties. And the last point on this, the actual timings for each of these custom events is shown just below the summary table for the test run. So let's quickly look over some scenarios and see what else we can learn. Now, you may have seen this pattern in previous slides I've shown, but I just haven't pointed it out to you. When running a test in Chrome, the resulting waterfall has a common pattern. This pattern is called the stair-step. The top step can be seen in red, the bottom step in black. So what's happening here? This is essentially a separation between the assets in the head and the body. It's a prioritization strategy Chrome uses to improve performance. Chrome will dedicate most CPU and bandwidth to getting the page head set up before then concentrating on assets in the body. This example under HTTP 1.1, notice the TCP connection at request 15. This request is for an image that is located in the body, but is being requested at the same time as assets in the head. So Chrome isn't completely ignoring the body, but resources in the head are the priority. So I mentioned earlier about the CPU graph at the bottom of the waterfall chart. So here's an example of what can happen to a waterfall chart when the device is CPU limited. It looks fairly standard until we look closely. Then we'll notice the gaps between the requests. These gaps on requests 24 to 26 show a large amount of inactivity that has a huge impact on performance. If we examine the CPU graph directly below these gaps, it points to the reason why this is happening. The graph is maxed out at 100% over this time period. But we see the opposite for the network activity. There's nothing really happening. Examining the browser main thread, there's some script parsing and execution in orange. There's some page layout tasks in purple, but nowhere near enough activity to cause the CPU issue. So something odd is going on with this test. I'm afraid I don't have an explanation as to why the CPU is so maxed out in this instance. It may be on a low spec device that was having particular issues for the test, but it shows how useful the other graphs can be when used in conjunction with the waterfall chart. So preloaded fonts is always an interesting topic to discuss. If done correctly, it can improve perceived performance, but you need to be careful, as it's also quite easy to make performance worse. So this is a very recent example of where WebPageTest came in useful, as it was very obvious that the browser was loading too many fonts, or the request seen in red. Here we see the waterfall graph for the new White House website. Highlighted in blue are all the fonts being downloaded by the browser. Notice the location of the top set of fonts in the waterfall. They are requested right after the HTML has been parsed on request number 1, but before the CSS has been requested and parsed on requests 8 and 9. This is a sure sign that these fonts have been preloaded. If we now turn our attention to the second set of fonts, notice how these fonts are initialized after the CSS has been parsed. Also notice the extension of these fonts. These are WAF files. Looking back at the preloaded fonts, these are WAF2 files. So we have a font mismatch here. WAF2 fonts are being preloaded, but WAF fonts are being used in the CSS. Examining the CSS, we can actually see the issue in the @font face rule. The WAF font source is placed before the WAF2 font source. Or to put it another way, the mistake with these two characters have meant the browser is having to download an extra 7 font files, or approximately 500 kilobytes of extra fonts. Now, this is such a simple mistake to make as a developer that without WebPageTest, you'd be very hard pressed to actually spot the issue. The image on screen shows a visual progress of the White House website before and after the fix went live, showing much improved performance. And it's all thanks to a WebPageTest waterfall chart. I have a post all about this specific waterfall on my blog if you're interested. And finally, an unusual waterfall that cropped up in a government service recently. And another shameless plug, I have another blog post all about this specific waterfall chart too. We use SpeedCurve to monitor our services at GDS. These tests run every day to look for web performance issues. On this service, we saw the number of fonts being downloaded literally double overnight from 3 to 6. Nothing had changed, no releases, no code deployed. It just happened randomly. Examining the graph, we can see the font size double. In fact, the historic graph data shows the issue being randomly happening and fixing itself many times in the past. If we look at this waterfall, it gives some insight into what's happening. Looking at requests 12 to 14 for the WAF2 fonts, we see this really strange set of gaps between the download chunks. Now, it took a while to figure out what exactly the issue was, but a long story short, we weren't serving the very origin header with our fonts. So the CDN cache was being poisoned and serving up the fonts with the incorrect headers. So a device was connecting, the headers for this first device were being cached by the CDN and then served to our test browser on another device. The browser was seeing these incorrect headers from the first device and immediately rejecting the fonts. We can actually see all this happening in the waterfall. Requests 12 to 14 are made for the WAF2 fonts. Very thin slices of data are received back from the server. These are probably the headers. The browser immediately cancels the request. And this is seen in the waterfall by the light red colors disappearing. Almost immediately after this happens, the browser makes a request to the fallback WAF versions of the fonts. This then doubles up the number of font requests and it increases the bytes being sent to the browser. The dark red patches that now look like they're floating is likely to be data that was already in one of the various buffers between the server and the browser and is already in transit, so therefore couldn't be cancelled. And this is just an example of how much information we can get from a waterfall chart once we understand some of the internals. Without SpeedCurve and WebPageTest, this would have been almost impossible to identify and fix. As we come to the end of the talk, you may be asking, where can I go if I want to find out more information? Here's a list of various resources if you want to find out more about WebPageTest. There's more shameless plugs in there from me, as well as talks from Pat Meenan and Andy Davies. I'll share these slides after the talk. So this talk is based on a blog post I've written called How to Read a WebPageTest Waterfall Chart. I did the research and pulled the information together for this post, but I've had lots of input from folks in the web performance community with corrections, additions, and general advice. So a big thank you to all these lovely folks. Their Twitters are listed and they're all worth a follow if you don't already. I hope you found this talk useful and thanks for listening.